So far we have laid a lot of groundwork before we can describe our first planner. We have seen how a planning domain describes a state space. We have seen how to define a planning problem, what constitutes a solution to the problem, and previously we have seen how to search through a search space. If we put all this together, we end up with a forward state space search planner, and that's what we will look at next. So here is the basic idea how state space search works. Namely, we want to apply standard search algorithms that we've seen before, like breadth first search, depth first search, or A star, you may remember, to a planning problem. And to do this, we need to define the search space, which may be different from the state space. But in this case, our search space is simply a subset of the state space that we define for the planning problem. The nodes in our search space correspond simply to world states. So the states that we have in our planning problem are nodes in our search tree. The arcs in the search space correspond to state transitions as defined by the operators and the actions that we execute as part of the plan. And a path in this search space corresponds to a plan, which is the solution we are looking for. More specifically, here is how we can define a planning problem as a search problem. So we are given a planning problem as a set of operators which implicitly define a state transition system. We're given an initial state and a goal description. These three components make up our planning problem. Then we can define the search problem as follows. For the search problem, we need an initial state, and we simply take the initial state from our planning problem. Then we need a goal for our search problem, and we define a goal test here, namely the test that S satisfies G. So the state that we're currently searching must satisfy the goal. Then we can define a path cost function for our search, and that is simply the length of the plan we're currently looking at. Implicitly, this means that all actions have equal cost here, and that is why the path cost function as the length of the plan works. And the final component we need is a successor function, and the successor function, denoted gamma of S here, is what we will define next. The successor function gamma of S for a single state is defined here. It is the set of all states gamma SA for all actions A that are applicable in this state S. So this set consists of all those states that can be reached by an applicable action from our state S. If I wanted to compute this, I would have to go through all the operators and find all the ground instances of these operators that are applicable in the state. Then I could apply those actions in the state, and I would get all the successor states here. This is how gamma of S is defined. We can extend this definition slightly. Suppose we are not in one state, but we are in a set of states. We know that we are in one of these states, and we want to define what states are reachable from any of these states. Then this is simply the union over any of these states of gamma sk. So we compute the successors for each of the individual states and build the set union, which is the result of gamma s as1 through Sn. This gives us the states that are reachable from any of those states that are the input to the function in one step. We can make this definition yet more general by naming the number of steps we want to allow. In the simplest case, we have gamma 0, which means we allow 0 steps. So if we're in any of these states as 1 through Sn and want to compute the states that we can be in after 0 steps, well, that's exactly the states we start in. If we don't do anything, we can't go to any other states. But in general, we want to allow m steps here, and we want to say initially we are in one of these states as 1 through Sn. And then we can apply a recursive definition of the function gamma by saying we apply this to gamma m minus 1. So we take the set of states we start from. We can go m minus 1 steps from these states. That is the input to this here. And then we can go one more step here. And that is then the set of all states that are reachable from S1 through Sn in m steps. So that is what we've defined here. We've defined the function gamma m, which maps a set of states to another set of states, namely exactly those states that are reachable in m steps from any one of the states given in the input. The transitive closure of this function then simply defines the set of all reachable states. So this is defined here. All the reachable states are simply the union of k from 0 to infinity of gamma k of s. So we start in our initial state, and we apply k steps from there. This is this set. And we can apply 0, 1, 2, 3, and so on up to infinity steps. And if we take the union of all that, that is all the states that are reachable from our initial state s. And that is the function gamma forward of s. And here is why I've given you such a complex definition. Because with this definition, I can very simply state when a planning problem has a solution. So we can state that a strips planning problem, defined by a state transition system, initial state and goal, or a statement defined by the operators and the initial state and the goal, has a solution if and only if the following holds. Namely, if we take the set of all goal states and we take the set of all reachable states and we build the intersection between these two sets, then this must not be the empty set. Or you can see it the other way around too. If this set actually contains an element, let's say a state Sg, then this state is in both these sets, which means it is a goal state and it is reachable from the initial state. And if there's a reachable state from the initial state that is a goal state, that means we have a solution to our planning problem. Now, this is all great, but you may wonder, when are we actually going to see a planning algorithm?